Hello and welcome back. So today in this episode we are going to study on 2D viewing. So let's see what is 2D viewing. Okay, we'll go move on to the introduction of 2D viewing. See, a graphics package allows a user to specify which part of a defined picture is to be displayed and where that part is to be placed on the display device. So any convenient Cartesian coordinate system referred to as the world coordinate reference frame can be used to define the picture. So for a two-dimensional picture, a view is selected by specifying a sub-area of the total picture area. So viewing is done in a sub-area, okay? So a user can select a single area for display or several areas could be selected for simultaneous display or for an animated sequence across a scene. The picture parts within the selected areas are then mapped onto specified areas of the device coordinates. Okay, so when multiple view areas are selected, these areas can be placed in separate display location or some areas could be inserted into other larger display areas. So transformations from world to device coordinates involve translation, rotation and scaling operations as well as procedure for deleting those parts that are outside the limits of a selected display area. So here we actually is going to view a 2D picture in a specified area. Okay, that is known as device coordinates. Okay, this is how it looks like. So this is the normalized space where we have a window. Okay, we have a WS1 window and WS2 window, which is completely known as a viewport. So from here, the first viewport WS1 window can be, that is window screen 1, that is known as WS1. So window screen 1 can be seen like this in monitor 1 and the window screen 2 can be seen in monitor 2. So from a window space, when we are viewing it separately from a sub area of the total area, we are calling it as viewport. So this is the viewing coordinate window. Okay, this is how we are performing or we are viewing a 2D picture or a 2D representation in a device coordinate system. Now let's see the viewing pipeline. A world coordinate area selected for display is called a window. So where we could display a world coordinate is known as a window. And an area on a display device to which a window is mapped. An area on a display device to which a window is mapped is called a viewport. In this now, so what is a viewport and what is a window? Okay. And the window defines what is to be viewed and the viewport defines where it is to be displayed. So what is to be viewed is defined in a window and where it is to be displayed is defined in a viewport. So windows and viewports are rectangles in standard position with the rectangle edges parallel to the coordinate axis. In general, the mapping of a part of a world coordinate scene to device coordinates is referred to as a viewing transformation. So viewing transformation is done by mapping a part of the world coordinate scene to device coordinates. The two-dimensional viewing transformation is simply referred to as the window to viewport transformation or the windowing transformation. Now let's see a figure. This figure, it shows a viewing transformation using standard rectangles for the window and the viewport. So this is a window where we have a world coordinates. Here we will be plotting all the coordinates in the window. That is why it is known as world coordinates. And here we have a viewport we have plotted only the device coordinates. Okay. So now we carry out the viewing transformation in several steps. This is the figure showing the step. First, we construct the scene in world coordinate. Okay, we are constructing the scene in world coordinate using the output primitives and attributes. Now, next, to obtain a particular orientation for the window, we can set up a two-dimensional viewing coordinate system in the world coordinate plane and define a window in the viewing coordinate system. That is being done in the second step. Now, the viewing coordinate reference frame is used to provide a method for setting an arbitrary orientations for rectangular windows. Once the viewing reference frame is established, we can transform descriptions in world coordinate to viewing coordinate. Okay, we then define a viewport that is in normalized coordinates in the range from 0 to 1. So, normalized coordinates are 0 to 1 and map the viewing coordinate description of the scene to normalized coordinates. And at the final step, all parts of the pictures that was outside the viewport are clipped and the contents of the viewport are transferred to device coordinates. Okay, so what we said earlier itself, that is from a window coordinate or from a world coordinate, we are transforming it into a device coordinates where we can only see the exact picture which is included in the sub area. Okay, we'll show it through a figure. Now, this figure illustrates a rotated viewing coordinate reference frame. This is a rotated viewing coordinate reference frame and the mapping to normalized coordinates. Okay, from 0 to 1. Normalized coordinates are from 0 to 1. We are mapping it onto a normalized coordinate frame. Okay. So, by changing the position of the viewport, we can view objects at different positions on the display area. Okay. Okay, also by varying the size of the viewports, we can change the size and proportions of the displayed objects. So, we can achieve zooming effects by successively mapping different sized windows on a fixed size viewport. So, we will be having a fixed size viewport from 0 to 1. There we can view different sized windows, okay, or the angles of different the size and proportions may vary. Okay, so viewports are typically defined within the unit square, that is the normalized coordinates. Okay, that is the unit square is this is a viewport. Okay, so once the scene has been transferred to normalized coordinates, the unit square is simply mapped to the display area. So when all coordinate transformations are completed, viewport clipping can be performed in normalized coordinates or in device coordinates. So now let's see the next topic, that is viewing coordinate reference frame. What is a viewing coordinate reference frame? Okay, the coordinate system provides a reference frame for specifying the world coordinates window. Okay, this is a figure which shows a world coordinate reference frame. Okay, a viewing coordinate frame is moved into coincidence with the world frame into two steps. Okay, so the first step is to translate the viewing origin to the world origin. See, this is the viewing origin. We are transforming it into the world origin, that is the normal origin position. Then rotate to align the axis of the two system. We will rotate it and align the axis of this two system by x, that it comes to y view y world and x view x world comes to the same axis. Okay, so then we need to establish the orientation or rotation of this reference frame. One way to do this is we are translating the viewing origin to the world origin and rotating it to align the axis of the two system. So these see. So first, a viewing coordinate origin is selected at some world position P0 equal to x0, y0. Okay. Then specify a world vector V that defines the viewing YV direction. Vector V is called the view up vector. So these unit vectors are used to form the first and second rows of the rotation matrix R that aligns the viewing XV YV axis with the world XW YW axis. So given V, we can calculate the components of unit vectors V as Vx Vy and U as Ux Uy for the viewing YV and XV axis respectively. Okay. Of two-dimensional transformation to convert world coordinates to viewing coordinates is MWC VC is equal to R into T. Where what is R? R is supposed to be the rotation matrix and T is the translation vector. Okay, where T is the translation matrix that takes the viewing origin point P0 to the world origin, and R is the rotation matrix that aligns the axis of two reference frames. Our next topic is window to viewport coordinate transformation. So once object descriptions have been transformed to the viewing reference frame, we choose the window extents in viewing coordinates and select the viewport limits in normalized coordinates. So object descriptions are then transferred to normalized device coordinates. First, we are having a figure here to illustrate that. So the figure illustrates the window to viewport mapping. So this is a clipping window and this is the normalization viewport, that is from 0 to 1. So in between the unit square only we can see the sub area of the window. Okay. So now see, a point at position XW, in the window is mapped into position XV, YV in the associated viewport. Okay. To maintain the same relative placement in the viewport as in the window, we require that in X direction, we can say that XW minus XW min by XW max minus XW min equal to XV minus XV min divided by XV max minus XV min. So because we are mapping, we are maintaining a same relative placement in the X direction, and that is marked as 1, and also in the Y direction, which is marked as equation 2. So let's see what we are doing in the Y direction. So same equation we are representing in Y direction also. YW minus YW min divided by YW max minus YW min equal to YV minus YV min by YV max minus YV min. From 1 we are getting the, we are equating it and we are cross multiplying it. By cross multiplying, we form the equation of XV from the equation. So XV equal to XV max minus XV min divided by XW max minus XW min into XW minus XW min plus XV min. Okay. Likewise, we are again forming the equation of same YV also. Okay. So we got an equation for XV and we got an equation for YV. So from each of the equation can be written as XV is equal to Sx into XW minus XW min plus XV min. Okay. And YV is equal to Sy into YW minus YW min plus YV min. So here Sx is XV max minus XV min by XW max minus XW min, and Sy equal to YV max minus YV min by YW max minus YW min. So here we can say that Sx and Sy are the scaling factors to scale from the window to viewport size, and XV min and YV min are translation factors which takes the scaled window coordinate to the corresponding location in the viewport. So this is how we are performing window to viewport coordinate transformation. Thank you so much.